Okay, so we've talked about the different types of bonding. Ionic bonding, metallic bonding, and covalent bonding, and how covalent bonding involves the sharing of pairs of electrons. And carbon is very good at forming covalent bonds. In doing so, carbon can form a large variety of molecules. Some of the molecules we talked about in the last lesson were polymers. And we talked about homopolymers, heteropolymers, and we gave several examples of polymers. And the take-home lesson so far should be that a variety of molecular structures, a variety of compounds can be formed by linking together atoms, especially through covalent bonding. And secondly, that the properties of the molecules depend upon the way the atoms are bonded together. In this lesson, we're going to talk about the properties of substances. In particular, we're going to talk about the existence of phases, solid, liquid, and gas phases. This will be a bit of a review because we've already mentioned solids, liquids, and gases. We want to talk a little bit more about these phases and mention how they are dependent upon the interaction between the molecules, what I sometimes call the stick'em. Because in certain phases, solids and liquids, the molecules want to interact with each other, and that causes them to exist in a solid or a liquid phase, whereas in the gas phase, the molecules do not interact with each other, and therefore they separate from one another. But we'll also talk about solids, liquids, and gases because it's important to understand the transitions between these phases, and we'll treat these transitions as something like chemical reactions. So again, to review, this slide shows a representation of solid, liquid, and gas phases of matter. In a solid phase, the matter has a fixed shape. There is this attraction between the molecules, holding them in place, holding them next to each other. In doing so, there can be long-range order, what we call a crystalline array or a crystal matrix, where it's almost like having one row after the other, but in 3 dimensions. Solids can also exist if the molecule is very large, just a very large molecule. This is what we call an amorphous solid. And large molecules such as cellulose in trees and a number of the polymers that we talked about in the last lesson are solids simply because they are large molecules. In a liquid, the molecules also interact with each other, but there is no long-range order. And in particular, the molecules are in constant motion. It is almost as if a solid is like a classroom with rows of desks, with students in the desk completely filling the classroom, whereas in a liquid it's more like students on a dance floor, moving around, interacting with each other, but no long-range order. In a gas, the molecules do not interact with each other in any appreciable way. They are in constant motion, just zipping around, bouncing off of each other. And in a gas, what is noteworthy is that the molecules will expand to completely fill the volume of the container. Now let's consider what happens if we try to compress each of these phases. On the left, I have something like a piston pushing down on the solid, and solids are not very compressible. That is, you can apply force, you really cannot compress them very much. Liquids also you can press down and you can compress them a little bit, but not a great deal. But in gases, if you applied a piston and you were to try to squeeze the gas, in fact, you would find that there is an inverse relationship between the pressure and the volume. The larger the pressure, the larger the force you apply to push down the piston, the smaller the volume. This is the basis for what is called the ideal gas law for gases, which we won't go into, but it just is one of the characteristics of the gas phase. Also, if you increase temperature, the volume occupied by a gas will increase. So this box summarizes: as pressure goes up, volume goes down. Now, while we usually talk about 3 phases of matter, it would be remiss of us not to talk about a 4th phase called a plasma. And this is because, in fact, 99.9% of the matter in the universe is thought to exist as a plasma. So why haven't we talked about it? Well, it's because plasmas exist like in the sun and stars. and plasmas only exist to a small extent here on planet Earth. Plasmids are transiently formed in lightning, plasma display TV tubes, or inside fluorescent lights, or inside certain lasers. That is, plasmas can exist, but only to a very small degree and only in certain situations here on planet Earth. So we haven't talked about plasmas, but in fact, if you consider the entire universe, plasma is probably the most important phase of matter. And in a plasma, the electrons and the protons of the nucleus, protons and neutrons of the nucleus, are separated from each other. And so you don't even have intact atoms in a plasma. Now, going back to the solid phase, and we said that there can be crystalline solids and amorphous solids. We generally find the crystalline solids to be a little bit more interesting because we like to think of things that are ordered. This slide shows depictions of what we think the crystal lattice of two compounds, salt and ice, ice of course being a solid form of water. The crystal lattice at the molecular scale is shown on the left, and then as you see to the right, the result of this basic crystal lattice, when you expand it into something on our scale, we get crystals of sodium chloride. Likewise, ice has a very ordered crystal pattern at the molecular level. When we expand it up to our scale, we see crystal patterns that look like things like snowflakes, which also have very interesting structures. The point is that the structure at the molecular scale determines the structure on the macroscopic scale, or on the scale that we experience. Now that we've talked about solid, liquids, and gases, let's talk about transitions between these phases, or what we call phase transitions. Now this sounds like it might be a complicated topic, but it's something you're very familiar with. Solid going to a liquid is what we call melting. And of course the reverse of that, if the liquid goes to the solid, we call that freezing. So see, this is not any more difficult than that. Liquid going to a gas we call evaporation. And the reverse, a gas forming a liquid, we call condensation. These are just the terms that we use, and you've used them. Now the last transition is one that you probably don't talk about every day, but if a solid goes directly to a gas, we call it sublimation. And the reverse of sublimation, when a gas goes directly to a solid, we call deposition. The box on the bottom right is what is called a phase diagram. And if you look at this, there are three general areas of this diagram. It's a plot of pressure versus temperature, but we'll get to that when needed. But if you notice, there are three major areas. One, which we have labeled as the ice phase space, one is the liquid or water phase space, and the other is the gas or water vapor phase space. Notice that the y-axis is pressure, and notice the number 1 on this axis. The reason that's important is because we actually experience 1 atmosphere of pressure. That is, the pressure around you, what your ordinary experience is, 1 atmosphere of pressure. And so if we start at 1 atmosphere over to the left-hand side of this diagram, which would be low temperature because the x-axis is temperature. So if we start off at low temperature, we would be in the ice phase of water. See, that's not so hard to understand, is it? And as we go to higher and higher temperature, and as we cross especially 0 degrees, 0 degrees on our temperature scale, and this is a centigrade temperature scale, as we cross 0 degrees centigrade, ice melts to water. And then water remains in a liquid phase until we get to 100 degrees, at which time it is converted to the vapor phase, water vapor, or evaporation. So this is what we mean by transitions between phases. As an aside, water is actually an unusual molecule in the following respect. When it freezes, it expands. And that is the basic reason for why ice floats when it freezes. Ice floats on a lake. And that turns out to be an important property for life on planet Earth. Now, is it possible to go directly from the solid ice form to water vapor without going through the liquid phase? Well, in fact it is, but at low pressure. So if, for example, instead of experiencing 1 atmosphere of pressure, we were in some other environment, for example on the moon, where the pressure would be much lower, we could go from ice to water vapor without going through the liquid phase. That is, we would be essentially crossing this phase diagram in this region. And this is the basis for what is called freeze drying. If you've ever heard of something being freeze dried, it's because you're removing the water vapor at very, very low pressure. Now, you may have heard of a particular substance called dry ice. Dry ice is solid carbon dioxide. And it's called dry ice because it goes directly from the solid to the vapor or to the gas phase without there existing a liquid phase. So how could that be? Well, in terms of phase diagrams, it's because the 1 atmosphere pressure on this phase diagram is located as indicated, and carbon dioxide, solid carbon dioxide, can go directly from the solid to the gas without going through the liquid. In fact, if you wanted to form liquid carbon dioxide, you would have to go to higher pressures. You'd have to pressurize the system in some way and then increase temperature and go from the solid to the liquid and then to the gas. So it behaves in a predictable way. It's just that its phase diagram properties are different from that from water and most other substances. Okay, we're again going to take a break to have a quiz or an exercise and then come back.